In just 48 hours, NASA has been secretly gearing up for an incredible event. An interstellar visitor hurtling along at 137,000 mph from a distant star system is set to zip by Mars at a distance of 29 million kilometers. Yet, there's a key detail they're keeping under wraps. Avi Loeb from Harvard has scored this visitor a solid 6 on his 10-point scale for possible extraterrestrial origins. That means a 60 likelihood it's artificial. Forget natural origins. Once you check out the latest images snapped by backyard stargazers, it'll be clear why experts in the field are totally freaking out. This thing isn't acting like your typical comet. It's spewing out pure nickel with 0 iron mixed in. That's unheard of in the wild. Such a separation only occurs in factory settings. Its composition is 16 times wilder than anything we've cataloged in comets before. The color shifted from red to green in a single night, plus the odds of its path being purely coincidental sit at 1 in 500. Now, things take a scary turn. Come late September, 3I Atlas will vanish behind the sun for a full 2 months, blocking our view right at its nearest pass on October 30th. Loeb proposes this timing might be deliberate, dodging scrutiny during its peak visibility or some other key moment. A few researchers suspect it could have already launched stealthy scout probes, tiny ones beyond our ground-based scopes that might arrive at Mars as we fixate on the primary body. More than 227 observatories around the globe have been monitoring it closely. They've gathered over 4,000 data readings, and each one amps up the mystery. Weighing in at 33 billion tons, this anomaly defies all logic. The numbers don't add up. We'd expect to spot thousands of tinier fragments long before encountering something this enormous. So what exactly is 3I Atlas? Over the coming hour, I'll dive into all the oddities, the confidential sightings, and the hypotheses that pros are hesitant to air in public. Because once October 3rd rolls around and the Mars probes swivel their lenses toward it, we could uncover real truths or stumble onto revelations that shake us to the core. If this hooks you like it does me, smash that like button, subscribe, and drop a comment. Where are you tuning in from? What's the local time? And share the strangest experience you've ever had. Chapter 1. Loeb's jaw-dropping 610 score. Loeb has just dropped a bombshell that's rattling the astronomy world. The Harvard star expert who back in 2017 floated the idea that Oumuamua could be alien hardware has now pegged 3I Atlas at 6 out of 10 for signs of intelligent design. Again, that's 60 odds against it being a random rock. And no, don't dismiss it outright. Grasp what flipped his view. This wasn't guesswork. It stemmed from hard evidence via the James Webb Space Telescope, Chile's Very Large Telescope, and Hubble imagery. Each revealed impossibilities. Webb caught 3I Atlas on August 6th, spotting a vapor tail that's 95 carbon dioxide with just 5 water vapor. That's 16 times drier and more intense than any comet we've tracked at that solar distance. Normally, these icy wanderers brim with water, not this one. Then, the VLT picked up unmistakable nickel signals in the emission's bright, distinct lines. But the twist? Absolutely no iron detected. Across decades of cosmic surveys, nickel and iron are inseparable partners. They're born linked in collapsing stars and blasted out as a duo in stellar explosions. Spotting nickel solo is akin to flames with no source. It's unnatural, yet routine in man-made processes like crafting pure nickel for aviation parts or high-grade alloys. The profile screams industrial output, not stellar junk. And the nickel output is ramping up fast. Back in July at initial spotting, the release was tame. By August, it surged 25 times higher. As it nears the sun, more of that metal is sublimating into gas. Loeb drew fierce backlash for hinting at otherworldly causes. Jason Wright from Penn State labeled his analysis careless. NASA's Tom Statler insisted it resembles a comet and behaves accordingly. Neither of these explanations accounts for the nickel absent any iron. They're also ignoring the unusually high CO2 levels and the path that only has a 1 in 500 shot at occurring by pure chance. Lowe concedes that his tech-based theory is mostly speculative. He notes the top possibility remains a regular comet, though most likely doesn't mean guaranteed. With his 6 out of 10 score, he's essentially admitting a 40 risk that our assumptions are off base entirely. The Mars Close approach on October 3rd should reveal more details. Should the HiRISE camera detect a core bigger than 5 km, matching his size estimates, the everyday comet idea falls apart. Interstellar space simply lacks sufficient rocky debris to send such massive items our way so often. Chapter 2. The backyard snapshot that went viral. Social platforms are buzzing over images that top experts refuse to engage with. Hobby astrophotographers are posting shots of C2019Y4 Atlas that defy comet norms. Rather than the soft, hazy aura one anticipates, certain captures reveal outlines, shapes, sharp boundaries that defy logic. Michael Shager and Gerald Raymond, esteemed non-pro observers, snapped C2019Y4 Atlas amid the full lunar eclipse on September 7th from Namibia. Their pics depicted the body shining emerald with a blue hue, evidently loaded with gases and detectable in blue and green bands. Experts have validated these shots they're authentic. Yet, it's the lesser-known enthusiasts, absent from official announcements, who've grabbed the so-called structured visuals now. Snaps spreading across Reddit, Twitter, and astroboards depict something firmer, more outlined under the vapor shroud, resembling an edged form over a nebulous haze. The expert reaction: quiet or swift rejection. Under scrutiny, they point to motion smear, imaging glitches, scope alignment flaws, fair points for snapping speedy, dim targets far below unaided sight. Blurring and warping happen routinely. But what intrigues here is this: the Atlas Discovery Scope measures just 20 inches across, typical for home setups. Serious amateurs often wield matching or superior kits, so why brush off odd formations from comparable tools without a proper look? On Reddit's astro communities, arguments rage. Folks pit photos against each other. Some display textbook comet traits, emerging coma and subtle tail. Others present tougher puzzles, dense hearts, uneven forms, pixel layouts clashing with usual star or comet blur profiles. Half the crowd yells, "editing foul," while the rest pushes for pros to redo the shots with pro gear to confirm or debunk. That effort's absent. Pros instead dive into discussions to debunk sans any pledge to inspect personally. A popular X post features what seems a tighter, sharper heart than Hubble's view. The shooter said it came via a 14-inch Schmidt Cassegrain, built from 50 stacked frames, routine for faint object hunts. Experts promptly blamed air turbulence, alignment slip, color fringing, whatever to wave it off. Not one proposed aiming big telescopes at those spots. None volunteered to validate the find, only to shut it down. What stands out as odd in this mess: NASA's Hubble shot from July 21st revealed a droplet-like dust shell with radiance stretching out front toward the sun. That's verified agency info, and it already bucks the rules. Comet streams ought to trail rearward, driven by solar breeze and light push. This one's aimed ahead. Professional astronomers described it as fascinating, enigmatic, and deserving of further investigation. Yet when hobbyists spot odd features during the same time frame, it's often chalked up to mistakes by the observer. Then, on August 27th, Gemini South snapped pictures revealing the initial signs of a genuine anti-solar tail trailing after the object. Clearly, between July and August, a shift occurred. Perhaps 3i Atlas began acting more like a classic comet, or maybe our perspective altered sufficiently to uncover what had been present all along. The majority of those amateur snapshots alleging strange formations were captured right in that July to August period, when the object deviated most from comet-like behavior. Even the expert observations highlighted irregularities at the time. And here's yet another detail that tends to fly under the radar. NASA's Sphere-X infrared space telescope examined 3i Atlas in early August and detected it merely as a point source. No expansive coma, no tail, just a solitary speck. That's hardly typical for comets in infrared wavelengths, where they usually exhibit widespread glow from heated gases and particles. But Sphere-X picked up none of that, just one intense dot. So a clear trend emerges. Experts encounter peculiarities they struggle to account for, while enthusiasts notice oddities dismissed as amateur blunders. Both groups are capturing the same entity in that peculiar interval when it wasn't resembling a comet at all. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are set to image 3I Atlas on October 3rd, employing cameras built for photographing Mars's terrain from mere hundreds of kilometers distant. But they'll be viewing this from 30 million kilometers away. ESA has already noted that they anticipate no stunning visuals. It'll span less than a single pixel in their instruments. Still, suppose the amateurs captured something legitimate. Suppose there's underlying structure hidden within the haze. These October views might not clarify it any better. We could require nearer access, superior tools aimed straight at it minus any atmospheric distortion. In reality, we're navigating with incomplete visibility. Pro telescopes operate on tight schedules with allocated slots, while amateurs enjoy more freedom but wield simpler gear. And in the space between, some bizarre activity unfolds that neither camp fully admits. Because if the hobbyists are onto something, if there's a form that defies standard comet shapes, then it's not mere optical illusions. It means challenging our assumptions about interstellar travelers. Chapter 3, the October 3rd, Mars Flyby, the details they're overlooking. In just 2 days, 3I Atlas will zip within 29 million kilometers of Mars. That might seem a comfortable margin, but consider this unspoken aspect. The minimum orbit intersection distance, the nearest approach to Mars's full path around the Sun, amounts to only 7 million kilometers. Avi Loeb termed this extraordinary precision. When a Harvard physicist chooses such pointed phrasing, it's worth heeding. The HiRISE camera on the Mars Reconnaissance Orbiter will photograph 3I Atlas on October 3rd at a resolution of 30 kilometers per pixel. That's sharp enough to distinguish the core from its encircling dust veil, precise enough to gauge the true reflecting surface area, and capable of verifying if this thing truly measures 5 kilometers wide, as Loeb's recent mass estimates propose. If it's indeed that sizable, the ordinary comet theory falls apart completely. Given the sparse supply of rocky debris in interstellar regions, we ought to have spotted about 100,000 diminutive interstellar bodies, akin to Oumuamua, before encountering one as hefty as 3I Atlas. Yet we've only identified 2 prior intruders, both minuscule by comparison. But this is where it turns truly unsettling. Loeb determined that if 3I Atlas released a Forerunner probe, a compact reconnaissance vessel advancing roughly 30 million kilometers in front of the primary body, that Scout could rendezvous with Mars on October. It could happen on the 3rd or sometime in the prior week. And now for the really scary aspect. Telescopes here on Earth struggle to spot anything under roughly 100 meters across when it's out near Mars. That's about the maximum size of every probe or spacecraft we've ever put into space, so any advanced Scout would basically be hidden from our view. This concept isn't quite as outlandish as it might seem. Suppose you were planning a voyage from another star to check out a solar system. You wouldn't risk one huge vessel all by itself. Instead, you'd launch a central carrier along with tinier scout drones, sending them out first to collect info on specific worlds, as the primary vessel takes a cautious route through the area. That's precisely the approach we'd take for something like that today, assuming we possess the means. Plus, the path of 3I Atlas lends a chilling credibility to the notion. To alter its course so it brushes right up against Mars, the thing would just need a modest speed tweak of 10 to 15 kilometers back in September, bringing the nearest pass down to nothing. For something built by intelligent beings, that's a piece of cake. But for your average comet, forget it, utterly unfeasible. Data from the Webb telescope shows that chunks of ice shooting off from melting comets top out at around Vogel's ejection velocity, way too slow to make the difference. ESA's Mars Express and the ExoMars Trace Gas Orbiter are set to examine 3I Atlas come October 3rd, employing a range of tools. Think sharp cameras, spectrum analyzers, and detectors for particles. These are built for probing Mars's ground and air layers, yet now they're getting redirected toward this intruder. From 30 million kilometers out, the gear aims to profile the comet's outgassing behavior and makeup. Yet there's an unspoken goal they're not shouting about. The setup won't merely snap pics of 3I Atlas proper. It plans to sweep the nearby void, hunting for whatever could be leading the way ahead of the core body scouting for those Forerunner devices. Loeb laid this out plainly in his online writings. Direct HiRISE to hunt for items ahead of 3I Atlas that swing nearer to Mars than the primary chunk. Should bits from 3I Atlas show up on Mars come October, stuff that natural vaporization and flinging couldn't possibly deliver, that'd scream artificial origins. The schedule feels off as well. 3I Atlas hits its tightest Mars pass precisely 7 days before it slips from our sight behind the Sun. Spacecraft around Mars give us that single clear chance, and poof, the thing fades into the Sun's blinding light for 2 full months. No sightings until December kicks off. Want to slip a delivery onto Mars without anyone noticing? This slot is ideal. Release the Scout right at the October 3rd skim, as ground-based scopes fixate on the big one. Meanwhile, the carrier ducks solar cover for 8 weeks, letting the Scout carry out its mission unchecked. NASA's Curiosity and Perseverance robots down on Mars might try peeking too. Even if the comet looks super dim from ground level, the Mars Reconnaissance Orbiter stands as our prime hope for close-up shots. Then comes the big what if. Suppose they spot evidence. If HiRISE grabs a shot revealing extra bodies, odd path changes, or hints of deliberate control, then what? Shout it from the rooftops right away? Double-check with more scans? Keep it under wraps? No one's mapped out steps for this kind of event, since it never crossed anyone's mind as a real possibility. The guidelines for spotting alien smarts zero in on broadcasts or laser pulses, not hardware, cruising the Sun's inner neighborhood. Come tomorrow, the truth emerges on whether those backyard stargazers caught genuine oddities. We'll learn if the nickel-lacking iron trait holds the implications Loeb suspects. We'll figure out if the 7 million kilometer bare minimum orbital overlap was pure luck or intentional engineering, or else we'll gaze at a standard comet core straight out of nature's playbook and watch all the wild theories crumble into awkward silence. Regardless, October 3rd, 2025 could well become a milestone etched in history. The moment we either verify 3I Atlas as a bizarre yet genuine interstellar comet, or the instant the world shifts forever. Chapter 4. The stunning revelation of nickel minus iron. Chile's Very Large Telescope has spotted an anomaly that defies natural laws. From the end of July through the end of August 2025, spectral scans uncovered neutral nickel particles emanating from 3I Atlas, prominent emission signals across various wavelengths, undeniable evidence of nickel vaporizing off the body's exterior as it nears the Sun. Yet iron was entirely absent, no hint whatsoever, not a single emission line in the typical ranges where iron ought to show. To grasp why this is utterly astonishing, consider this. Nickel and iron are inseparable partners in the cosmos. They emerge side by side from identical nuclear furnaces within giant stars. When those stars detonate in supernovae, both metals are hurled into the void as one. They solidify into cosmic dust particles jointly. They embed themselves in asteroids and comets in tandem. Across every celestial fragment humans have examined, from Earth-fallen meteorites to mission-retrieved samples, nickel and iron always occur in consistent proportions. Spotting one devoid of the other is akin to discovering oxygen sans electrons. It upends the core principles of universal composition. The VLT squad, headed by scientists unlinked to Avi's Boulder hypotheses, released their results with measured phrasing. They proposed the nickel could stem from nickel-carbonyl substances, hypothetical molecules that might endure in frigid interstellar realms. Such materials are unstable, disintegrating under UV radiation to yield nickel and carbon monoxide. Still, even the VLT experts conceded this scenario would be groundbreaking, unseen in any comet from our solar system, undetected amid the stars, a speculative rationale for data that cries out for answers. What compounds the issue? The nickel output isn't steady. Upon 3I Atlas's initial sighting at 39 AU from the Sun back in July, the emission level hovered near 1021. Notable, yet not cause for panic, come late August, now at 285 AU, it had surged 25 times higher, 25-fold more nickel pouring from the surface over a mere month. As this entity draws nearer the Sun, its metallic outflows escalate sharply. And this ramp-up doesn't mimic the smooth patterns of standard comet vaporization. It's explosive, abrupt, as if targeted heating is methodically evaporating some component. AV highlighted the unspoken truth others shied from voicing outright. Here on Earth, we routinely isolate nickel from iron via manufacturing techniques. Refined nickel powers elite alloys in aviation gear, gadgets, power cells, any tech demanding precise heat or magnetic traits. The pattern emerging from 3I Atlas aligns with factory-grade nickel yields, not the balanced mixes of space's raw materials. Detractors pounced right away, accusing Loeb of data manipulation, bias-driven interpretation, and wishful thinking. Penn State's Jason Wright was especially cutting, dismissing the industrial analogy as deceptive and pseudoscientific. Yet critics sidestep a key puzzle. If natural carbonyls are the source of this nickel, then where's the iron? Iron crafts analogous unstable variants. Iron pentacarbonyl is a staple in lab studies. Should conditions have formed and safeguarded nickel carbonyls across eons in the interstellar void, identical setups would forge iron carbonyls too. Both should manifest, but solely nickel emerges. The VLT data further noted a sharp uptick in cyanide output, with hydrogen cyanide and associated molecules surfacing in the A gas cloud surrounding 3I Atlas expands at speeds that ramp up dramatically as the body draws nearer to the sun. Loeb proposed that the shift in hue from red to green, noted by backyard stargazers, could tie directly to this surge in cyanide. Such a substance isn't rare among comets at all. It represents a typical mix of carbon and nitrogen present in numerous frozen celestial objects. Yet the sharp escalation in its output, along with the abrupt rise in production that aligns with the nickel release, indicates some underlying connection between these phenomena. The most intriguing aspect here is the insight it offers into the makeup of this entity. Suppose the bulk of its material consists of carbon dioxide frost, laced with just hints of water, as Webb identified, and assume the exterior is venting nickel and cyanide in ever-growing quantities. Then, the reactions we're witnessing diverge entirely from those of anything born within our solar system. Typical comets originating from the Oort cloud or Kuiper belt brim with water, because they coalesced in zones where frozen H2O could endure. The balance between water and CO2 mirrors the heat levels and makeup of the protoplanetary disk that birthed them. In contrast, 3I Atlas flips that proportion on its head. It prioritizes CO2 with scarcely any water. This points to formation in an utterly alien setting, orbiting some foreign star. Alternatively, it hints that the object might not be a product of nature whatsoever. A further option lingers that few dare to explore in depth. Imagine if 3I Atlas stems from natural roots, perhaps an age-old comet hailing from a distant stellar realm, yet it has journeyed across the void of interstellar space long enough to transform its outer layers chemically. Bombardments from cosmic radiation, collisions with tiny dust particles adrift between stars, reactions unfolding in the frigid emptiness approaching absolute zero. 7 billion years under such relentless assault might warp a surface's makeup in bizarre ways. Perhaps the iron-free nickel trait holds true, but the true cause lies in a gray area bridging ordinary comet and engineered vessel. An idea beyond our current grasp, since we've yet to examine something this ancient from such remote origins. Come October, fresh sightings should clarify matters as HiRIS photographs 3I Atlas from its perch in Mars orbit. Spectral readings from Mars Express and the ExoMars Trace Gas Orbiter will snag extra spectral signatures, expanded details on nickel generation, further gauges of cyanide and CO2 emissions, tighter limits on the true nature of this enigma. For the moment, based on our current findings, 3I Atlas is spewing out nickel at levels fit for factories straight into the cosmos, all without a trace of iron, and no one offers a convincing account rooted in natural causes for it. Chapter 5. The vanishing trick concealed by the sun. Toward the end of September, 3I Atlas slips from view. Not obliterated, not nudged off course, just obscured. From our planet's vantage, it swings too near the sun for any scrutiny. Over a pair of months spanning late September to November, Earthbound scopes forfeit their clear path entirely. The thing fades into the blinding solar glow. What renders this schedule particularly dubious is the following. 3I Atlas hits perihelion its nearest solar pass on October 30th, 2025. Precisely when comets hit peak frenzy, as sunlight's warmth sparks the fiercest venting, exposing the deepest secrets of their build and innards. The prime slot for unraveling this puzzle's essence, and it's utterly blocked from sight. Our world sits squarely on the sun's far flank. Avi floated the notion that this might be no mere chance of celestial paths, but a calculated maneuver. Should 3I Atlas seek to dodge in-depth scrutiny by terrestrial instruments amid its most luminous frenzied period, this path delivers spot on. It ducks behind 150 million kilometers of searing hot gas right at the pivotal instant. NASA, alongside fellow agencies, scramble for countermeasures. The Parker Solar Probe, now looping tight around the sun to probe its outer atmosphere, could snag a peak should schedules sync up. SOHO, the solar and heliospheric observatory that monitors the sun non-stop for solar storms, stands poised as 3I Atlas streaks by, through its field of view. However, the cameras on SOHO are built for studying the sun, not spotting dim comets. The object will probably be too faint amid the sun's intense glare. As for Jupiter's icy satellites, the JUICE Explorer is positioned on the opposite side of the sun from Earth right now. It's employing its high-gain antenna to block heat, limiting any data sends. JUICE plans to scan 3I Atlas in November with its instruments and sensors, yet that information won't reach us until February 2026, long after the event. We're essentially in the dark right now during the key phase, as October 30th unfolds behind a veil of stars. What might occur over those couple of months? Should 3I Atlas prove natural, nothing out of the ordinary. It warms up, releases gases more vigorously, and could even split if heat causes fissures in its core, reappearing in December a bit reduced in size and subdued in activity as it retreats toward deep space. But suppose it's artificial, harboring any tech elements at all, then those 2 months offer an ideal chance for hidden maneuvers. Things like orbit tweaks, launching probes, path shifts, or any thrust-based moves that would stand out to ground observers if only we had a view. Calculations show that a speed boost of merely 10 to 15 kilometers in September or October could redirect 3I Atlas dramatically, targeting Mars, Venus, or Earth with cargo. For a genuine comet, that's out of the question, vaporizing frost yields at best a nudge of 0.5 kilometers. Yet for an engineered craft with engines, it's a breeze. Another scenario feels even more disturbing. What if this vanishing is deliberate? What if 3I Atlas skips its December comeback? Imagine it leveraging the sun's close approach to slow down, settling into a lengthy oval path around the sun, turning into a fixture in the inner solar system. We couldn't detect that until December, when it's due to pop back into sight. And if it fails to appear on schedule, if the path has shifted markedly, that screams artificial thrust, deliberate design, purposeful action. This line of speculation has roots, though not from interstellar visitors. Back in 1986, the Soviet Vega missions zipped by Halley's Comet and uncovered surprises. The core was much blacker than expected, bouncing back just 4 of the sunlight hitting it. Prior to Vega, experts figured comets were shiny, frozen bodies. In reality, they're pitch dark, layered in organics and grit, with ice hidden under a tough outer shell. That finding reshaped our view of comets up close. It came from direct flybys. Earth's distant watches had led to total misconceptions. For 3I Atlas, we're stuck with remote monitoring in this vital stretch, guessing from sparse info, risking flawed conclusions. We stay clueless until December 3rd, when it should slip out from the sun's shadow and light up for Earth telescopes again. Hobby stargazers are gearing up already. Scopes globally are booked for initial December looks. All are eager to catch the first glimpse of its return. They want to check for alterations in appearance, shifts in vigor, or if the route aligns with forecasts. If it veers off, if 3I Atlas exits perihelion altered in course or features, then the core astronomy world must confront the man-made idea head-on, not as some outlier notion from a debated researcher, but as a real prospect demanding scrutiny. This blackout also blinds us to possible breakups. True comets can shatter close to the sun, heat splits the core. Built-up gases inside trapped volatiles can eject large fragments from the surface. We've observed this process on various comets that approach the sun too closely. Should 3I Atlas break apart, we wouldn't witness the event itself. Instead, we'd only observe the consequences come December. Rather than a single intact body, there would be numerous fragments. Extended debris paths, altered spin, and splitting would actually bolster the idea of it being a natural comet. Man-made artifacts rarely disintegrate due to solar warmth. Unless the splitting is deliberate, unless what appears as disintegration is really a release mechanism with smaller components detaching from the primary structure, each aimed at distinct destinations within the inner solar system. Such a notion feels straight out of sci-fi, yet so does the absence of iron alongside nickel. So does the flawless alignment with the ecliptic plane. So does the precise Mars encounter at 2.7 million km. Each bit of evidence we gather renders those sci-fi ideas a tad more plausible. The object's reappearance in December will reveal key details, not the full picture perhaps, but valuable insights nonetheless. For now, we linger in uncertainty, wishing the entity that reemerges matches the one that vanished behind the sun. Chapter 6. The unusually hefty body, 33 billion tons. A fresh study has just surfaced, stirring unease among astronomers. Richard Chloe, Peter Vey, and Avi Lowe examined 422 sightings of 3I Atlas from 227 global observatories, spanning May 15th to September 23rd. They monitored its path with remarkable accuracy, contrasting the real orbit against expectations from gravitational forces alone. And they uncovered a startling result. 3I Atlas exhibits virtually no extra-gravitational motion. Even with intense venting spotted by Webb and other instruments, even while shedding hundreds of kilograms of substance each second, its course strays by less than 15 meters per day, squared from a gravity-only trajectory. This implies it's extraordinarily heavy, way beyond what its luminosity indicates. The equation is simple enough. When a comet vents, the ejected matter functions as a small thruster. It nudges the comet mildly from its path. The degree of offset hinges on the volume of material released and the comet's overall weight. Lighter comets with vigorous venting display clear non-gravitational shifts. Heavier ones with identical venting show minimal effects. 3I Atlas is releasing vast quantities of gas. Webb detected 129 kilon per second of carbon dioxide, 6 kiloliters of water, and 14 kilon per second of carbon monoxide. That's considerable output. It ought to cause evident path alterations, yet it doesn't. The shift falls beneath measurable thresholds, suggesting the body's mass is immense enough to counteract that thrust. Estimates set the minimum at 33 billion tons, or 33 trillion kg, with a core at least 5 kilometers wide. This renders 3I Atlas 3 to 5 orders of magnitude denser than the prior two interstellar visitors. Oumuamua was likely just hundreds of meters in size at largest. Borisov may be a kilometer. This one is 5 times broader in width, equating to over 100 times the volume and heft. And that's the issue. Drawing from interstellar void knowledge and tallies of rocky or icy debris amid stars, items this size ought to be exceedingly uncommon. So uncommon that we'd expect to spot about 100,000 tinier interstellar intruders before encountering one as substantial as 3I Atlas. But we've identified only 2 prior interstellar objects throughout recorded history. It's akin to hitting the jackpot thrice consecutively. Feasible in stats, but so unlikely that suspicions arise about the odds being manipulated. Lowe suggests this indicates a purposeful route. If 3I Atlas was intentionally directed toward the inner solar system, if its course was selected instead of haphazard, the improbability vanishes. We're not drawing at random from the cosmic wanderers. We're hosting an intentional arrival by something. Critics argue that this notion is absurd. They highlight how our detection technologies have advanced significantly over the past several years. The Atlas survey responsible for spotting 3I Atlas didn't reach full capacity until about 10 years ago. Prior to that, we just weren't searching with sufficient intensity. Naturally, we're detecting additional interstellar bodies these days. At last, we possess instruments powerful enough to identify them. That's a valid counter-argument. The Vera Rubin Observatory, operational since 2025, identified more than 2,000 asteroids during its initial 10 hours. Our capacity to spot dim, rapidly traveling items has surged dramatically. Perhaps in the coming years, we'll uncover scores of additional interstellar intruders, and the statistical issue will sort itself out. However, that fails to address the matter of its mass. Regardless of enhanced spotting methods or discovering extra interstellar items, the distribution of sizes ought to align with forecasts. Abundant tiny bodies, scarcer mid-sized versions, and rare giants. That's the standard pattern across astronomical populations. Tiny asteroids vastly outnumber big ones by a ratio of millions to 1. 3I Atlas defies this norm. It's the biggest we've encountered to date, spotted well before we've logged the multitudes of tinier ones that statistics suggest should abound. The absence of non-gravitational propulsion further eliminates some theories. Certain researchers propose that 3I Atlas could be a loosely aggregated pile of debris, scarcely unified by feeble gravity. Were that the case, the release of gases would dismantle it. The thrust from those ejections would surpass the weak gravitational hold, causing the thing to break apart. Yet, it's staying intact. It endures even amid considerable material shedding. This implies either a sturdy unified core or some force uniting it more robustly than mere self-gravity. Observations from Mars on October 3rd could clarify the dimensions. Should HIRIS distinguish the core from its surrounding dust haze and gauge the light bouncing off the solid part compared to what's diffused by nearby grains, we'd obtain a more accurate figure for the actual core's width. Should it exceed 5 kilometers, the conventional interpretation grows unsustainable. Another idea that hasn't received wide consideration is this. Suppose 3I Atlas is enveloped in an expansive, hazy veil of ultrafine particles, with much of the observed glow stemming from that debris instead of the core proper. Then the core might be far tinier, invalidating the mass estimates. Yet Webb and Spherex examined it in the infrared spectrum. Infrared penetrates dust to expose underlying firm structures. Spherex viewed 3I Atlas as a compact point, not a sprawling haze. This indicates no vast particle sheath is hiding a diminutive core. Most of what we observe is the body in its essence. Thus, we return to a 5 kilometers core boasting no less than 33 billion tons, exhibiting virtually no non-gravitational thrust amid intense gas emission. A body that defies statistical likelihood, entering on a path with just 1 in 500 chances of being random. The evidence continues to accumulate. Every new measurement renders the ordinary account a bit more dubious, still feasible yet progressively forced, demanding escalating assumptions, additional flukes, and ever more exceptional circumstances. Chapter 7. Chemical Anomalies. The 95CO Puzzle. The James Webb Space Telescope examined 3I Atlas on August 6, 2025, via its near-infrared spectrograph. Its discoveries upend our expectations for interstellar comets' makeup. The vapor tail around 3I Atlas comprises 95 carbon dioxide and merely 5 water. That's an extremity 16 times beyond what's anticipated for a standard comet so far from the Sun. All comets from our own system that we've analyzed are dominated by water. They originated in the frigid outskirts where water ice prevailed as the chief sublimating substance. Carbon dioxide exists as well, but in far lesser proportions. The proportions mirror the formation temperatures and compositions of the protoplanetary disk from which these objects arise typically features a certain chemical makeup, but 3I Atlas flips that script entirely. It's essentially a chunk of dry ice with almost no water content at all. This points to its formation in a radically different setting, around a star boasting a unique elemental mix within a disk exhibiting varied temperatures and pressures far removed from the conditions that shaped our own solar system. Martin Cordner, lead researcher on the Webb observations, remarked that this represents one of the greatest carbon dioxide to water ratios recorded in any comet to date, not merely odd, but truly groundbreaking. Yet the composition grows even more peculiar. Webb picked up notable amounts of carbon monoxide and carbonyl sulfide as well. Such a mix implies the body developed in an intensely frigid setting, possibly chillier than the farthest edges of our solar system. Certain scientists propose that 3I Atlas could have emerged from a molecular cloud zone or been flung out from a planetary setup positioned much more distantly from its host star than our Kuiper belt. Adding to the intrigue is the shift in hue that backyard stargazers captured. Back in July and the start of August, sightings revealed 3I Atlas surrounded by a reddish haze. That shade often signals the presence of organic materials, intricate carbon-based structures that soak up blue wavelengths while bouncing back red ones. Nothing out of the ordinary for comets. However, by September 7th, amid a full lunar eclipse, images from Michael Jagger and Gerald Raymond captured it shining a vivid green, edged with blue. The switch appeared abrupt, almost instantaneous. While green-hued comets aren't rare, their glow stems from diatomic carbon particles in the envelope snagging UV rays from the sun and releasing green fluorescence. Prior exams in August by experts at Kitt Peak Observatory painted a different picture. They determined 3I Atlas to be one of the comet's poorest in carbon chains with minimal levels of diatomic carbon, precisely the stuff responsible for that emerald shine. So what allows a comet so scarce in diatomic carbon to flare up green all of a sudden? Avib theorized the hue shift could link to the sharp uptick in cyanide output noted by the Very Large Telescope. Under specific circumstances, cyanide materials can yield greenish tones too. That said, it sparks yet another puzzle. Why the explosive surge in cyanide generation? Data from the VLT indicated hydrogen cyanide releases climbing sharply as 3I Atlas drew nearer to the Sun. Rather than a steady release typical of comet venting, it spiked exponentially, as if some internal material was undergoing heat-driven changes at a quickening pace. Stephanie Millam of NASA's Goddard Space Flight Center, involved in the Webb data analysis, posited that 3I Atlas may possess a baked outer layer. Eons spent cruising interstellar voids, battered by cosmic rays and starlight, might have reworked its exterior chemically. In this way, carbon dioxide could have formed or built up via these influences, yielding its quirky surface traits. This idea holds water. After all, we've yet to examine anything this ancient 7 billion years surpasses the age of our whole solar system. Imagine what eons at near absolute zero in the starless expanse could do to frozen matter. Still, it falls short of accounting for every oddity. The nickel-heavy iron-light profile defies simple surface effects. So does the absence of extra push from outgassing. Each quirk might make sense on its own through natural means, but clustered together, they weave a tapestry that's tougher and tougher to wave off. Compounding this is the Spherex finding, which depicted 3I Atlas as a mere pinpoint emitter, devoid of any spread-out glow. Infrared instruments pierce dust veils to expose heat signatures from thawing ice and stone. Spherex ought to have detected a broad, hazy radiance from carbon dioxide ice turning to gas over the surface. Instead, it registered just a tiny, focused infrared hotspot, aligning with a fairly dense, solid body. That result clashes with expectations. This could deviate from standard comet behavior, or it might indicate that the object possesses exceptionally odd thermal characteristics. Maybe its exterior is extremely shiny, reflecting solar rays back into space to avoid warming the core. Maybe a protective coating blocks heat from seeping in. Maybe the core rotates at such high speeds that warmth spreads out evenly without triggering much evaporation. Alternatively, it could be venting gases differently than expected. What we see as evaporation might actually be a completely different phenomenon. The composition analysis further hints at the possible birthplace of 3I Atlas. Its minimal metal content, along with abundant hydrogen and frozen materials, points to origins in a galactic zone where stars formed in the distant past. Think of the Milky Way's dense outer layer, filled with ancient stars that haven't accumulated many heavier elements. Simulations suggest it formed 7 to 11 billion years back, turning it into a survivor from a time when our galaxy looked nothing like it does today. Should 3I Atlas prove to be a natural body, It serves as a snapshot of the early universe, a fragment of ancient frost bearing traces of chemistry from eons prior to Earth's formation. That feature by itself would render it the most precious scientific discovery in observation history. Yet the makeup still doesn't align perfectly. The prevalence of carbon dioxide makes sense. The absence of water can be rationalized. The presence of cyanide fits too. Even the shift in hue has a plausible cause. Every element offers a feasible everyday interpretation that tweaks our theories a bit without shattering them. The issue lies in how they all converge. It's the cluster of oddities showing up in one single entity. It's the slim odds of these exact traits aligning randomly. Data from November and December promises to shed more light. As 3I Atlas swings out from the sun's shadow, Earthbound observatories will snag new spectral readings, additional emission features, further molecular clues, and tighter limits on its makeup. Plus, contrasting the chemistry before perihelion with that after will reveal if the sun's proximity altered any core aspects of how this thing acts. Chapter 8. The Backward Tale That Defies Logic. On July 21, 2025, the Hubble Space Telescope snapped the sharpest view yet of 3I Atlas. The results flew in the face of fundamental comet science. The photo displayed a droplet-like envelope of particles, yet the illumination stretched out in front of the body, sunward. No clear streamer trailed it in the direction opposite the sun. That's completely reversed. Normally, comet streamers get driven from the sun by stellar winds and light pressure. They ought to trail away from the sun, giving that familiar curved-back look we link to comets. But 3I Atlas displayed its luminous face aimed sunward, lacking any evident streamer trailing behind. Jav Loeb and his associate Eric Kito released the sole study in peer-reviewed journals, trying to account for this reversed streamer. They proposed the leading shine could stem from grains propelled in front of the core via some hidden force, though they conceded it was guesswork. No solid process exists to generate a sun-facing particle haze on a typical comet. Fellow skywatchers brushed off the finding altogether. They argued the shine wasn't a reversed streamer, merely blur from Hubble pursuing the speedy traveler. The scope trailed 3I Atlas across the sky, streaking faint stars in the frame. Perhaps the leading shine arose from that pursuit blur. However, Hubble's data handlers are experts at correcting for motion artifacts. The star trails stand out clearly. The leading shine isn't a trail. It forms a clear zone of intensified light with sharp outlines. Were it mere motion blur, it would mimic the star lines. It doesn't. Later in August, the Gemini South Observatory grabbed updated photos employing its multi-object spectrograph revealed something unexpected. 3I Atlas had formed a genuine tail, a faint teardrop-like extension in the anti-solar direction trailing the body, precisely where one would expect a comet's tail to appear. Thus, from July 21st to August 27th, a notable transformation occurred. Perhaps the body began acting like a typical comet, or maybe our observational angle altered sufficiently to uncover a feature that had been hidden by the surrounding dust envelope all along. The Hubble snapshot from July captured 3I Atlas at approximately 4 astronomical units from the Sun. By contrast, the Gemini observation in August occurred when it was nearer, at about 2.6 astronomical units. Proximity to the Sun implies greater solar warming, increased sublimation, and possibly heightened dust release. It's reasonable to suggest that the tail hadn't yet materialized in July and only became visible as the object's activity ramped up. However, this fails to account for the leading illumination. Conventional comets lack vivid auras directed sunward. Instead, they feature comas, roughly spherical envelopes of vapor and particles encircling the core. While the coma might shine more intensely on the sun-facing aspect due to vigorous sublimation there, it wouldn't produce a forward-directed radiance in front of the body's path. Another intriguing aspect of the Hubble view raises questions. The dust sheath stretches roughly 3,000 kilometers around 3I Atlas in every direction. Calculations indicate that for a 10-kilometer wide nucleus, the particle concentration at 3,000 kilometer distance would be thinned out by a factor of 90 relative to levels close to the surface. Such a drastic reduction makes it remarkable that the sparse material remained detectable by Hubble. This implies either vast quantities of dust generation, highly reflective grains, or peculiar light scattering conditions. The Gemini observations further highlighted spectral differences. Various bandpass filters exposed distinct features. In ultraviolet, the structure seemed more condensed, whereas in red and near-infrared, the dust halo appeared more expansive. This aligns with standard scattering traits, where fine grains preferentially diffuse blue wavelengths and coarser ones handle redder light. Yet it also suggests an uneven mix of particle sizes. Smaller grains cluster near the core, while bigger ones distribute outward. This arrangement might reveal insights into dust expulsion mechanisms, swift tiny particles versus more leisurely large ones, mirroring classic cometary dynamics. That said, the spin rate adds complexity. Measurements indicated 3I Atlas completes a rotation every 16 hours, which is leisurely for an object of its scale. A 10-kilometer nucleus spinning that slowly achieves equatorial speeds of just around 1 meter. That's insufficient for centrifugal ejection of dust into orbit. Therefore, outgassing from sublimation must drive the release via gas drag. On the sunward flank, carbon dioxide vaporizing into space would entrain dust particles. Analysis of the Hubble data, however, pointed to grains traveling at roughly 20 masses far exceeding rotational velocity but matching acceleration from sublimating gases. Now, consider this. If dust launches at 20 metaswaa driven by carbon dioxide venting, and if the body sheds 129 kileliters of that gas as observations detected, then dust output ought to be considerable, likely in the tons per some interval. Such volume should yield a prominent tail, a luminous elongated feature evident in observatory photos. Yet the July Hubble frame showed none, merely the sunward sheen and a hazy coma. One explanation could be that the grains are minuscule enough for solar radiation pressure to propel them ahead before a standard tail can coalesce. Sunlight's radiative force can outpace gravitational tug on submicron particles, potentially shoving them forward of the nucleus. But that scenario would generate an anti-tail, not a forward glow. The structure doesn't match expectations. One alternative is that solar ultraviolet radiation is electrically charging the dust, causing it to interact with the sun's magnetic field. Electrically charged particles act unlike neutral ones. They can get concentrated or scattered by magnetic forces, leading to peculiar formations. Observations from NASA's SPHEREx mission only deepen the mystery. It detected 3 Atlas as a mere point in infrared, without any surrounding glow. No coma, no tail, just a single spot. Yet Hubble revealed clear extended features. The key difference lies in the wavelengths used. Hubble captured visible light. SPHEREx focused on infrared. Dust scatters visible wavelengths but radiates heat in infrared, depending on its warmth. Should the particles near 3I Atlas be exceptionally chilly cooler than anticipated at that solar distance, they'd appear faint in infrared, despite shining brightly in visible light. This implies the material isn't absorbing sunlight effectively to warm up. Perhaps it's extremely reflective, deflecting rays before they can transfer energy. Or it might consist of substances with odd heat retention qualities. Clarity on the tail will arrive in December as 3 Atlas swings out from the sun's glare. New data from various observatories across different spectra will reveal if the tail has grown, if it resembles typical cometary streams, or if it continues displaying odd traits that defy standard theories. Chapter 9. The 1 in 500 path alignment. 3I Atlas follows a backward path tilted about 175 relative to the ecliptic. That might seem drastic, but it boils down to this. The body travels nearly in the orbital plane of the planets, only in reverse. It's slicing through the solar system along the same thin disk where Earth, Mars, Venus, and Jupiter circle, yet heading the wrong way. The odds of such alignment occurring by chance, 1 in 500. Typically, interstellar visitors to our system arrive from arbitrary angles. The cosmos is three-dimensional, with no favored direction. If these comets represent random ejecta from distant stars, they ought to approach from every possible vector, some over the ecliptic, some under, some sideways spread evenly over the sky. But 3I Atlas arrived almost precisely matched to the planetary paths, deviating just 5 from the ecliptic. That's feasible, yet remarkably unlikely. And inclination isn't the only factor. Its route swings 3I Atlas near several worlds. It zips within 30 million kilometers of Mars on October 3rd. It draws reasonably close to Venus. Then, in March 2026, it nears Jupiter at 54 million kilometers. A single near miss isn't noteworthy. Space is vast, and many paths graze planets accidentally. However, the full set, the ecliptic sync plus several planetary brushes, slashes the random probability sharply. Lowe's analysis pegs the joint likelihood of these alignments happening coincidentally at about 1 in 500, improbable enough to spark thoughts of intentional origins. For a purposeful scout of the inner solar system like 3I Atlas, a route skimming key planets makes perfect sense. You'd prioritize the ecliptic, home to all the action, the inner rocky worlds, most satellites, the asteroid zone, zones ripe for potential biology. Such a path suits an exploratory craft. Skeptics counter with detection bias. We spot 3 Atlas precisely because its approach allowed discovery. Countless interstellar wanderers might traverse the outer system on erratic courses, invisible to us due to distance and dimness. The detectable ones must, by definition, venture nearby. Objects passing between the Sun and Earth make sense for detection. Our tools are geared towards spotting things in the inner solar system, where our observatories are focused. We could be overlooking most interstellar objects that linger in the outer zones, yet that doesn't account for the precise alignment. Among those that come near the Sun, the majority wouldn't follow the ecliptic path. They'd typically show high inclinations, slicing through the planetary disk at sharp angles. The near coplanar path of 3I Atlas with the planets stands out as odd, even among the ones we can detect. Another intriguing feature of its path involves the orbit itself. 3I Atlas follows a hyperbolic trajectory with an eccentricity around 6.16, indicating it's speeding past escape velocity. It's not tied gravitationally to the Sun. It arrived from interstellar space and will head back there. However, we can rewind the orbital path. By reversing the mechanics, scientists trace its origins. The math points to the thick disk area of the Milky Way, likely from a stellar system aged 7 to 11 billion years. That's remarkably old, predating our Sun and solar system. If 3I Atlas originated around such an ancient star, it may have journeyed through space for billions of years. The exposure to cosmic rays, chemical changes, and immense age set it apart from prior samples. Its route across the galaxy reveals more. Subtracting the Sun's pull from its speed, 3I Atlas was cruising at roughly 58 kilometers in interstellar space before arrival. That fits the profile for thick disk objects. The speed aligns with predictions, but the timing of entry doesn't. 3I Atlas reached the inner solar system in mid-2025, right when our spotting tech hit the mark. The Vera Rubin Observatory activated. Atlas achieved full ops. SphereX launched. All the gear for analyzing an interstellar guest was ready. Coincidence or deliberate schedule? An advanced society dispatching a probe might time it for when the target has the means to notice and examine it, show up when scopes can probe makeup and plot paths, initiate contact when the observers grasp the implications. It echoes sci-fi, yet remains plausible. Any group mastering interstellar journeys could scout distant systems remotely. They'd scan for tech signs, radio waves, city glows, air contaminants, markers of progress. Earth has emitted radio for over 100 years. Our tech traces have been detectable for generations. If 3I Atlas responded to those signals, the schedule clicks. Naturally, this assumes interstellar voyages work. Some culture cracked sending craft over light years, targeted us, masked it as a comet. Heavy speculation. Still, the odds sit at 1 in 500 for that exact planetary plane match, brushes with several planets, timed to our study readiness. The March 2026 Jupiter flyby will clarify. If 3I Atlas sticks to the forecast nearing at the projected range without shifts, it bolsters the natural origin. Orbits objects influenced solely by gravity follow foreseeable paths without any unexpected twists. But when anomalies appear, when the path shifts in manners that gravitational influences from planets can't account for, that's when issues arise. At that point, we must account for whatever redirected it, and conventional rationales dwindle fast once gravity and gas emissions are ruled out. Chapter 10. What's on the horizon? The decision draws near on October 3, 2025. That's just tomorrow. The HiRISE camera on the Mars Reconnaissance Orbiter will aim at 3 Atlas during its flyby at a distance of 29 million kilometers, achieving 30 kilometers per pixel clarity. Precise enough to distinguish the core from its surrounding dust veil and sufficient to gauge surface extent while limiting the true dimensions of this entity. Should the core prove to be 5 kilometers across or bigger, the probabilistic dilemma turns unavoidable. We ought to have spotted thousands of tinier interstellar visitors prior to encountering one of the scale. Standard theories demand ever more elaborate happenstances. ESA's Mars Express and ExoMars Trace Gas Orbiter will monitor it concurrently, employing spectrographs and imaging devices across various bands from diverse tools and viewpoints. Among all the Mars missions, this will yield humanity's sharpest examination of an interstellar visitor to date, and we'll hunt for advanced scouts items preceding 3 Atlas that might arrive at Mars as we track the primary form. HiRISE will survey the nearby void. Should something anomalous materialize, or if several entities emerge where only one was anticipated, the discussion shifts dramatically right away. Next follows the anticipation phase. 3 Atlas slips behind the Sun from our earthly vantage in late September. Visibility vanishes. The body attains perihelion on October 30th, its nearest solar brush, concealed from scopes by 150 million kilometers of blazing solar atmosphere. A pair of months in the dark, a span where unforeseen events could unfold unseen. Path corrections, satellite releases, break up any developments in that interval remain unknown until December, when the object reappears. Ground telescopes anticipate rediscovering 3 Atlas on December 3rd. Hobbyists globally are gearing up, major facilities are booking slots, all seek the initial glimpse of the object returning from its solar closest point. And all will contrast the after-perihelion data against pre-encounter records. Has luminosity varied? Has gas release ramped up or tapered off? Crucially, does it align with projected positions? If 3 Atlas reemerges on an altered path, if its orbital path has shifted inexplicably beyond solar and planetary pulls, that signals drive systems. That hints at artificial origins. That's the moment doubters must weigh other possibilities. Chemical analysis will reveal further insights. New spectral scans in December will check if the nickel-lacking iron trait endures, if carbon dioxide still prevails, if fresh spectral features emerge absent before perihelion. Heat from solar proximity could modify outer composition noticeably. If it splinters, that bolsters the ordinary comet idea. Everyday comets occasionally shatter close to the Sun under thermal strain. We've observed such with comets like Shoemaker-Levy 9 prior to its Jupiter strike. Breakup would seem routine, barring if it appears deliberate. If segments detach neatly and veer to varied targets, then breakup turns into dispersal. In March 2026, the Jupiter Rendezvous arrives. NASA's Juno probe, now circling Jupiter's poles, might catch sight of 3 Atlas at 54 million kilometer range. Juno carries imagers, analyzers, and sensors for particles. Instruments built to examine Jupiter could also help analyze this interstellar guest. Debates have arisen about whether the Juno probe might adjust its path for a nearer view. However, with restricted propellant and a scheduled mission conclusion, diverting resources to pursue an extraterrestrial body rather than focusing on the gas giant would spark significant debate. Yet, should the data from October and December uncover genuinely bizarre features, the argument for rerouting Juno gains strong scientific merit. The ESA's JUICE mission plans to conduct its own scans in November, although the information won't reach us until February 2026 because of transmission lags. JUICE sits farther out, positioned on the Sun's far side from Earth, employing its dish as a thermal barrier. Bandwidth for sending data remains constrained until it repositions itself. Thus, we're amassing observations over several months via various probes at diverse spots throughout the solar system. Come spring 2026, we'll possess the most thorough collection of information ever compiled on an interstellar visitor. That compilation will either validate 3I Atlas as a peculiar yet ordinary comet from a distant stellar neighborhood or compel us to confront the possibility of an actual visitation. Researchers are gearing up for either outcome. In confidential talks, stargazers are pondering protocols should signs of artificial origins emerge. Who makes the announcement? How do you substantiate bold assertions prior to disclosure? What does it mean for safeguarding our planet if additional such intruders appear? No formal guidelines exist, as few anticipated this turn of events. SETI guidelines target radio transmissions and deliberate signals, not tangible artifacts disguised as icy wanderers. The nearest parallel involves protocols for declaring microbial life on Mars or Europa. Meticulous checks, expert scrutiny, and several separate validations before any official reveal. But those steps presume extended periods, months or years for review. 3I Atlas is speeding onward and exiting our system. To investigate it thoroughly, choices must come swiftly. Certain experts push for a pursuit craft. Dispatch a compact satellite to meet 3I Atlas prior to its departure past Jupiter's path. Capture detailed photos, collect material from the vapor trail, assess magnetic influences and particle outflows at close range. The challenge lies in the schedule. Even a swift vessel would require months to close the gap. By the moment approvals and budgets align and the device assembles and lifts off, 3I Atlas would have departed long ago. These cosmic drifters travel at high speeds. Windows of opportunity span mere weeks, not extended timelines. This span from October through March holds utmost importance. It's our sole shot to acquire insights on the third verified interstellar arrival before it slips away into the interstellar expanse. Post-March, it'll grow too remote and dim for in-depth scrutiny. We'll track its dimming trail, squeeze every scrap of knowledge from the readings we secured, and then pause. Await revelations from our breakdowns that might explain the oddities through ordinary means. Await the arrival of further interstellar arrivals bearing akin traits. Await whether the odds even out or intensify. And even should the evidence point to a commonplace source, even if each peculiarity receives a standard rationale, the notion lingers. A 60 chance of artificiality leaves a 40 chance of nature, and 40 isn't nothing. The cosmos has caught us off guard previously. Black holes, cosmic acceleration, worlds beyond our sun, ripples in spacetime. Every breakthrough unveiled realities we hadn't foreseen and scarcely comprehend. 3I Atlas could represent yet another jolt, perhaps something innate but profoundly atypical, so unforeseen that it upends our theories and broadens our grasp of potentialities. Or it could mark the grandest breakthrough in a landmark event in humanity's timeline, the inaugural verified encounter with alien technology, signs that isolation in the cosmos is an illusion, confirmation of extraterrestrial societies capable of star-spanning voyages. Revelation is imminent. The information arrives shortly. October 3rd, December 3rd, March 2026. Dates destined to reshape our reality.